Hey Calc 3 class, I'm going to start doing a few more examples each time as requested. So I'm going to do this double integral, but because it is defined with circles, again this is the telltale sign that you're going to use polar coordinates. So I've got a little picture here of what this looks like I've made in GeoGebra. So right up here at the top I've got our function 2xy. So that's this surface that we see here that dips down below the plane when x and y are opposite signs in quadrants 2 and 4, and it is above the plane in quadrants 1 and 3 that we're seeing. Okay, and then down here I've got our domain defined. So this is a circle of radius 2 defined parametrically. Alright, this is a circle of radius 5 defined parametrically. Now it's only between 0 and pi over 2 because that's what our problem says. Okay, in the first quadrant. So first quadrant would mean that we are between 0 and pi over 2 for our angle measure. Now what I've got down here, I haven't got it added yet because I wanted you to see our domain. So it's all the stuff in between those two. So this is where the curve actually hits up on the surface. And if you notice how I've got that defined, if you ever wanted to do this in GeoGebra, you just have to define your function. So f of xy up there at the top. And then when you plug in, you define the circle parametrically, 2 cosine 2 sine, and then you just say f of 2 cosine 2 sine. This is f of x and y. This is saying plug that parametric path into the function. So I'm replacing x and y with what I'm using to get x and what I'm using to get y, and it's plugging it in there for me, 2 times x times y. So it's giving me that surface. Now I'm going to take the surface away because what we're trying to find is the volume of this crazy looking shape right here. So if you can imagine all that clear stuff above it, like up to where the surface was. So it's following that surface path up to that point down here, and then this connected vertically all the way along that red line there. That's the shape that we're trying to find the volume of. Alright, now how do I do it mathematically? Well, I'm going to set up my integral in polar coordinates. So I'm going to get our function 2xy. Remember, x is r cosine theta and y is r sine theta. So when I set this up, I'm going to have a 2 r cosine theta and then another r sine theta for the y. And then remember, when we do polar, the differentials isn't just dx dy, it's r dr d theta. When we have polar coordinates, we have to add this extra r in there when we do this. Okay, and now I got r dr first. Our radius is going from a radius of 2 to a radius of 5. And then theta, in this case we're just quadrant 1, so it's 0 to pi over 2. We're not going all the way around like we have in some of these examples. Alright, so there is my integrand. I'm going to simplify it a little bit nicer. So this is going between 0 and pi over 2. Alright, and then this is, if you notice, I've got between, oops, not 2, 5. Alright, I've got 1, 2, 3 r's, so that's r cubed. And then I've got, if you look right here, I have 2 cosine theta sine theta. Alright, and if you'll recall from your trig days, alright, and so I'm going to make that into, instead of 2 sine theta cosine theta, I'm going to make it into the sine of 2 theta. Just because it's a single trig function rather than multiple trig functions. Alright, and then dr d theta. Okay, all the r's have been gobbled up into this r cubed, and then the 2 sine theta cosine theta is that double angle formula for sine. Alright, so the first thing we're doing is with respect to r, so this is going to become r to the 4th over 4, and that's still sine 2 theta. It's like a constant when we're integrating with respect to r. Alright, and I'm integrating from 5 down to 2. Alright, and then I got a 0 to pi over 2 here, and d theta. Okay, now I'm plugging in 5 into this thing, so that's 5 to the 4th power, which is 625 fourths. Alright, and then minus, when I plug in 2 to the 4th is 16 over 4. Alright, and then again, that's all being multiplied by this sine of 2 theta integral. And I can put it, I'm putting it outside if you're paying attention to it. It's a constant, so I'm just pulling it out of the integration at this point. So sine 2 theta d theta. Alright, 625 minus 16 is going to be 609 fourths. Alright, and then the antiderivative of sine of 2 theta. Alright, so I got sine of 2 theta. The antiderivative, whose derivative is sine 2 theta? It's negative cosine 2 theta. Alright, but because I would chain on this 2, and I don't have it, I'd have a 1/2 out there. Alright, then I got a pi over 2 down to 0. Alright, so I got this 609 fourths out here times, when I plug in pi over 2, I get the cosine of 2 times pi over 2, which is the cosine of pi. Alright, the cosine of pi is negative 1, but I got a negative on the outside here, so I'd have a positive 1/2. Alright, so a negative times a negative is a positive, and then 1 times the half is a half. When I plug in 0, I get the cosine of 0. Alright, 2 times 0 is still 0. Cosine of 0 is 1, so this is negative 1, but we are subtracting. So negative 1/2 would be positive 1/2. And so we end up with 609 over 4 times 1, which is 609 over 4. Alright, let's check our work. This is Wolfram Alpha, and I am going to type in here double integral. It'll pop up, and I'll click on that. And then it'll ask me, what is your function to integrate? Now I'm going to tell it to give me the domains, because this is a definite integral. Alright, what's my function to integrate? I'm going to say it is this is when I switch it to polar. So when it became this thing right here, this is what I'm going to feed into Wolfram Alpha, because I need it to have the same differentials as it does the limits. And notice we started off with x and y, but we quickly switched things to polar, so it needs to be in this polar form. So r cubed sine 2 theta, 2 to 5, 0 to pi over 2. Alright, so I put in r cubed sine, I put just t for theta because I don't have theta as a key on the keyboard, so just use t, and that's very common when you're changing it, checking in your work in Wolfram. So the weird thing is, variable 1 is your outer integral, variable 2 is your inner. Okay, so it's kind of reversed to the way that we did it. We did dr d theta. So this is doing the outer first, so theta 0 to pi over 2, and then the inner. The way you can check that, it doesn't matter here because we had constant in both lower and upper limits integration. But just know here, when you compute it, it'll show you a picture of what it's computed. So notice there's our dr on the inside and our dt, or d theta, on the outside. So you can get a kind of a matchup to see here that you've done it correctly. Alright, there's our answer. There's the 609 over 4, which is what we got. So again, that's a way you can check your work on these with Wolfram Alpha.